That's, that's what happens when I don't have a full 5-minute break transition. Thank you again. This is the last panel you'll have to see me on today. This one that I'm introducing now is still in the ecosystem effects section, but focus more on oceanographic processes. For this particular panel, we have Ruth Perry, who's a marine scientist and regulatory specialist at Shell, and very recently involved with Shell New Energies and the Mayflower offshore wind project off of Massachusetts. We have Josh Kohut, who's a professor and co-founder of the Rutgers Are You Cool Lab, very knowledgeable of ocean observing systems and the application of that data. We also have Hans Burchard, who's a professor at the Leibniz Institute for Baltic Sea Research in the Department of Oceanography and Instrumentation in Germany. And Ole Peterson, Dr. Ole Peterson is who's with DHI. DHI, and has extensive experience in meta-ocean and circulation modeling, both numerically and physically. And Dr. Ole Peterson is working with BOEM right now on a hydrodynamic modeling study for the Mid-Atlantic Bight. So I wanted to kind of lead us off with maybe Ruth and Josh both giving a very brief, like, why do we care about oceanographic processes? I was thinking, Ruth, maybe from a engineering perspective, why this is important, and then Josh, perhaps from the ecological perspective.
Great, thanks, Brian. Thanks for everyone for joining in today and listening. And I'm very excited to participate on the planning committee on the developer side and really initiate some of the conversations around these topics. By background, I am a physical oceanographer, so the oceanographic process piece and how that interacts with the biology and the ecosystem effects is a passion on my science side, and then figuring out how to bridge that into the developer side, where we can use this information to inform our planning, but also use this information to figure out how we can address these issues and these scientific questions using the offshore wind structures themselves. There's a paramount opportunity that we have here to look at some of these issues based on the information and the data that we're collecting, whether that be buoys or things like autonomous systems, but also how do we might use these structures themselves to instrument them as platforms of opportunity. That's something that we have done in the oil and gas side of the house, especially in the Gulf of Mexico. However, it's unique here because we don't have the amount of structure in the water, and then based on the way that these are going to be built, they essentially create their own ocean observing grids, and those can be really important to resolving some of the temporal and spatial scales around oceanographic processes that we need to understand at a regional level and then at a very localized level as well. And given the time frame that these projects are collecting data now to the point where they would be decommissioned, it provides an opportunity to do that over a very long time scale, 20 to 30 years. And because of that, that helps us to address some of the time scales that are really critical to mesoscale or microscale oceanography. So I hit on that. The other side from the engineering is obviously offshore wind is coming in to address changes in climate. And we're not going to get into necessarily that side, but if you think about climate changes in terms of oceanographic processes, being able to resolve those from localized scales like weather and ocean heat and ocean currents, all of that's going to be very important. And all of that you'll hear later with my fellow panelists on how that interacts with the biology. And then the roles of key features like the cold pool. You heard in the last panel, we have to look at the effects and the local effects at the structures themselves, but what are they going to be affecting outside of the areas where the wind farm is. And the cold pool is one of these really important physical features that influences things beyond the cold pool itself. And so we have to figure out how to merge that with the work that's going to be done in the wind farms. And I won't pretend to be an expert at cold pool. That's certainly my colleague Josh talked about more of that. But how all of this feeds into the engineering and the technical design work is these are structures in the water. And so all of these things that you see on the list, there's a feedback effect in terms of how are the structures themselves going to be maintained and operate over long periods of time, not just the turbines, but the monopiles, the jackets, all of this information in terms of warming, cooling, scour, we have to use in our engineering design for the stability of the structures and look at that not only at local scales, but very long time scales and try to model and predict what the changes of oceanographic processes might have on the integrity of the structures. So that's really what I'm looking at. So how do the structures impact oceanographic processes, but also how do the processes themselves impact the structures? And so, you know, that feedback loop is really important. And then, you know, on the side of that, how can we use the structures to collect the physical oceanographic data that we need? Being able to look at flow and turbulence and mixing and stratification is an impact on sea surface temperatures. So we can structure these turbines with sea surface temperature, salinity instruments that really help us start to define the scales of flow, turbulence, stratification, mixing that we need to know in order to resolve how physical oceanography might be changing. So I'll leave it at that and pass it over to Josh to get more into the details around these topics. Thanks, Brian.
No problem. Josh, just a quick, if I don't know if your camera, see your camera on.
I'm here.
Oh, you're there. Okay. No camera though? That's fine. Oh, there you are.
No, I
Yeah,
have the
I see
camera.
you. I see you. I see you. Yeah, so just a kind of a, yeah, just a big, broad overview.
Yeah, no problem. I dressed up today, so I had to make sure I turned my camera on. You know? So yeah, thank you, Ruth and Brian, for that introduction. And my background is in physical oceanography, particularly in the areas of coastal oceanography. And it's a fascinating topic. And what we're considering here in this panel and in the breakouts that follow is what are the impacts of facilities like you see on the screen, the wind turbines, on physical processes. And we're considering processes from above the ocean surface all the way down through the water column to the bottom. And these are really important because, and granted I'm biased as a physical oceanographer, but the physical setup of the ocean and even the marine layer above is critical to a lot of the ecology in the region. And this is true in coastal systems and open water systems. And what we're considering here is the structure of the ocean, the layering of the ocean, the features that exist that Ruth mentioned. All of these things potentially impacted by the presence of any structure offshore. We're interested in the wind fields above because the boundary, while we see a boundary there in the surface of the ocean, the physical setup really sees no boundary. The conditions above the ocean have dramatic impacts on what's happening below the surface and vice versa. And so we're going to consider topics here because those processes have big impacts on what the ecology is doing. The ecology depends on the physical movement of certain water types, the prey, whether it's the prey or the actual species, and we'll get into that as we get into the session. And so the reason it's in the ecosystem effect is because the physical oceanography and the physical meteorology are integral parts of the habitat for many of these species.
Thanks, Josh. That's a great segue into the next slide, where we're going to be kind of, getting into, what we know and what we don't know in regards to the effect of these offshore wind facilities on horizontal flow and turbulence. And actually, before I leave that last slide, thanks to Jennifer Dreyer, this is actually the Seabow installation off Virginia. So we have, Block Island Wind Farm there. This is the two turbines that are now operational off of Virginia. Anyway, so Ole, I'll turn over to you to maybe walk through a little bit about horizontal flow and turbulence, and what we've observed, and what you think we need to know.
Yeah, thank you, Brian. Yeah, my name is Ole. My background is kind of environmental engineering. I've been working in marine environment for many years, mostly with modeling, and we have supported, say, maybe 80% of the offshore wind installation in the world today, and we are still involved in many of these installations. So we have a broad insight into effects and problems and challenges that provides for the industry and for the environment. So one of the things we looked at that has been, as we say here, when you place a turbine in the water, of course, there is an immediate downstream effect. You can see the wake, and you can see the mixing, as you see on these satellite images here, where the one on the left is basically, I think it's turbidity that is exposed to the surface, so it can be seen from the satellite. And it's from the London area. We are actually forecasting conditions here. And one of the big challenges here, you may be able to see that in the big waves, you can see internal structures is kind of big sand waves that are affecting the seabed. So we'll come back to that a little bit later. We have been looking at the effects both on the waves, on the wind, and on not on wind itself, but how the wind affects the water environment inside the park. And we can see, for example, that the fact that you take out energy from the wind, it does have an effect on the stresses, on the forces on the surface, and thereby on the waves and on the circulations. It's a little bit complicated because it depends very much on the atmospheric conditions. If you have, say, convective conditions, then the effects are small, but if you have stable conditions, then there can be quite substantial effects. But when we look at it, maybe just...
you want me to stay on the other side, or
yeah, please stay. I think Hans will take over here. But it's just that we have looked at the effect on waves. Of course, there's a direct effect, but if you look, for example, wave impact on nearby coasts, we have seen in the southern part of Denmark that the effects on erosion and coastal erosion are very minimal. So there is only a small effect from these. So, but maybe take the next slide, and then Hans can continue from me here. I think he's the one behind that.
All right, well, thanks for that. Thanks for including me here. I'm Hans Borchardt, a physical oceanographer in Germany, doing coastal oceanography, lots of modeling, turbulence modeling, and so on. And then, of course, it's quite logic that you also have to deal with effects of offshore wind farms on vertical mixing and stratification. Specifically in the German waters, we have a lot of such installations on the Baltic Sea side as well as on the North Sea side. If you look to the upper right panel, you see the principle we are looking at. It's a nice sketch made by Jeff Carpenter. The basic thing is that you have a density stratification, and that stratified water moves towards a structure, for example, as a tidal flow, and then the structure exerts a turbulence, generates turbulence in the water column. So you have a high turbulent kinetic energy level that then kind of increases the potential energy of the water column, which will lead to mixing and kind of decrease of stratification. I have for you here two examples of pretty different mechanisms. The left one is from the North Sea, a very recent study by Schulze et al. Jeff Carpenter is also part of that. And it looks a little bit like a small stamp collection to you, but if you go to the left little map, the greenish one, it shows an offshore wind park, exactly that one, in the southeastern North Sea, actually, where they did a number of field studies. There's this MP1, it's one cylindric foundation where they did a study. And if you look into the very lower left, then you see actually the ship track. So the flow is coming from the upper left to the lower right. And they kind of meandered through the wake of the structure. And in the lower panel, you see the result from some CTD observation. They had a CTD chain, so lots of different temperature sensors, one in the water column. It's in May, so it's still pretty well mixed, but you see temperatures going from 10 degrees more near the bottom to kind of almost 11 degrees at the surface. And these blue bars show the times when they pass the wake of the cylinder. And what you clearly see is the effect of vertical mixing in the sense that you get decreased stratification. They reproduce that also with a so-called LES model, large eddy simulation model, where you actually resolve the large energetic eddies. And that's shown in this yellowish, bluish plot. What you see here is kind of the surface view of the sea surface temperature. And it's for a relatively weakly stratified scenario where you see that in the wake, you have a decrease of the sea surface temperature, which is significant. And that's the effect of mixing. Well, another study which I was part of is shown on the right side for the Western Baltic Sea. There the situation actually is different. I don't know if you have any of such sites in the United States, but it's pretty non-tidal. You see here a map between of the waters between Denmark, Sweden, and Germany of the Western Baltic Sea. These are the connecting waters between the salty North Sea and the brackish Baltic Sea. And the major mechanism here is that you have an exchange flow, so salt water near the bottom entering the Baltic Sea. That's shown on this transect to the right, and this black bar. The red arrow shows you kind of a classical inflow that would be near the bottom and of salty water, and you would then have an outflow of less salty water near the surface. And the question is, if you install lots of wind farms there, would this exchange between the Baltic Sea and the North Sea be reduced? And that exchange is very important because it would kind of ventilate the bottom waters of the Baltic Sea, which are typically anoxic. We ran two experiments, one with the wind farms existing in 2010. That's just these few little numbered red dots there, red areas. And then to see kind of to work on a worst case scenario, we put huge hypothetical wind farms that these kind of big rectangles. So what we studied, for example, is the effect on the inflow at that transect shown on the right. So a typical situation, long-term average salinity would be, you see at that so-called Bornholm channel, you see a range from 15 in red to 7.5 salinity in blue. And the decrease of that you get with the realistic wind farms is shown in the middle. The realistic decrease, say, it's kind of between an increase actually of 0.05 and a decrease of 0.08 PSU, which is far, far below, of course, natural variability. And in the worst case, you could get up to kind of a long-term decrease of 0.5 PSU, which would mean some less ventilation of the Baltic Sea. But we didn't find any tipping points or so. I mean, if you put more wind farms, then you got more mixing and you get less ventilation. That's look to us a little bit as a linear process. If you go to the next slide, you see another one. Yes, that's what we basically know, that vertical mixing is increased and certification is decreased downstream of a wind turbine. We can also quantify that for a single, say, installation, more or less. What we don't know actually is, and what we really need to study are, what are the larger scale effects? And of course, we know that these larger scale effects depend very much on the location where you are. So, I mean, just by studying one wind turbine, you cannot really say how this is kind of changing your regional area. So it depends on the location. It depends on when you studied that in the year. So it depends on the season, and certainly also of the wind farm layout and design, right? And I think another effect is, I think Ole comes to that a little later, or someone else comes to that later, are these wind wake effects, which are at least as important, I guess, as these hydrodynamic effects. And what we really need to know and to study is actually the interaction between these effects of the water and the effects on the wind. Thank you.
Great. Thank you, Hans, very, very much. Yeah, I think that was something that last bit on the wind wake and the boundary, I think that was something Josh brought up in his overview as well. And with that, I'll segue back to Josh with our case study on the Atlantic coast. There's been a lot of interest in the Mid-Atlantic cold pool in particular as a stratified system and how offshore wind may interact with that. So Josh?
Yeah. Thank you, Brian, and thank you, Ola and Hans, for that introduction, because the processes that they were talking about, we want to think about in the areas along the East Coast that are currently being considered for development. And in the global map there, what I'm showing is the difference in surface temperature of the ocean water from summer to winter. And so where you see purples and blues, that's where the ocean temperature doesn't change very much. So you see the high latitudes, it's always cold, no matter if it's summer or winter. In the tropics, it's always warm in most areas, except some of the upwelling areas. It doesn't change much, but you see hotspots along the East Coast of North America, as well as the East Coast of Asia. And those show just how unique some of the ocean conditions that we have in our region are. To have an ocean that goes from 28 degrees Celsius in the summer, a surface ocean from 28 degrees Celsius in the summer to 4 degrees Celsius in the winter, is very unusual. And what it does is it sets up a feature that's unique to the Mid-Atlantic Bight called the cold pool. And many have been talking about it recently, but essentially what it is as that surface ocean heats up to the nice warm summer conditions, the bottom doesn't get the benefit of that solar heat, and it keeps 8 to 4 degree water consistently on the seafloor all the way through August and September, really until this time of year when fall storms mix it all up. And that's when the bottom is the warmest. The bottom temperatures are the warmest. And so I show here on the right just what a typical cold pool would look like. The stratification, or the difference in density of the cold pool compared to the water above, is dramatic. So that temperature change going from 8 degrees Celsius, around 40 or so degrees Fahrenheit, up to 28 or warmer surface waters in the 70s to 80s range in Fahrenheit, happens within about 3 feet or a meter. So that gradient is very, very strong, and it leads to a really dynamic feature that the ecology depends on. It's a great thermal refuge, particularly for bivalves and other benthic species that depend on that cold water niche throughout majority of the year. And so what we know about the potential impacts of offshore wind on this unique feature is that it is dynamic and that it is a critical habitat. And that makes it a real challenge, because when we start looking at what other impacts might be, we have to include the natural variability of this highly dynamic feature. Modeling studies, some that were shown, show that turbines can influence the turbulence and potential mixing that could impact the cold pool, but what we haven't done and what we need to do is to consider how those studies might apply to the uniqueness of the cold pool. And not just think of the cold pool as one static feature, but think of it as a dynamic feature that sets up in the spring each year. It stabilizes and maintains itself through the summer, and then it ultimately breaks down in the fall. And so the big questions around this are what impacts might a single turbine, a wind farm, and a series of multiple wind farms have on these different processes associated with the cold pool, because they all have ecological connections.
Great. Thanks, Josh. Really appreciate bringing that U.S. context to some of the studies that we just showed from the North Sea and the Baltic Sea. Next, I'll turn it over more to scour. So we're talking, I guess, more that local effects that we were talking about earlier today, scour and sedimentation. And Ole, I'll turn it back over to you to maybe talk about some of the work that you've done on looking at scour.
Yeah, thank you. The scour is a little bit more, say, confined process relative to the cold pool or the larger scale circulations. But scour, you can say that's an issue for a developer who wants to have a monopile standing in the water for 30 years and as a stable platform. It can be a very important issue to protect the seabed, because if it's dynamic, if it's sand, it may be washed away into some extent. So that's the challenge for the developer, you can say, and do that in a costly and robust way. From the environmental side, of course, there are impacts when you install it. You have to dump a lot of rock and will change the seabed. It's also a possibility, you can say, because you will introduce some variation in many environments where you have stable rock-based sediment that may be inhabited by other species. So there may come a change in the ecology somehow. We have seen that in many places. And finally, also, there's the little larger, you can say, impact. That is how potential changes to the sediment transport, and that goes both for the sand and also for, say, finer sediment like mud and suspended material that may be affected in a similar way as, for example, Josh described, that changes in the hydrodynamics, in the turbulence, in the flows, that may also affect and change the sediment transport ways and give some impacts in that way.
Thanks, Ole. Can you talk maybe a little bit more, or Hans or others, specifically on the relationship between what we see in scour and pile diameter and water depth? We saw on that very first slide, the London array, where you could visually see some of the suspended sediment where the monopiles were up on the shoals. Can you give maybe a little bit more context on that relationship?
Yeah. Normally, it's a fast process. Normally, these scour holes, they can develop on over days, maybe after installation, and they are normally stable. If you have say in a river, you can get where it's a constant current across. You can get quite deep scour holes, but in the sea, where you have both waves and currents at the same time, the currents, they seem to dig the hole, while the waves, they backfill basically. So there is a balance here. So normally, if it quickly finds a balance in terms of depth and volume, and then it stays there. So what we saw on the picture on the satellite image, it's probably not from the scour, because that's stable. What we saw was maybe mixing behind the monopile due to the turbulence that mixes up deeper waters that has a larger content of sediments. Because there is the natural sediment that passes by here will also be stratified. There will be more sediment close to the seabed than up in the water column. If you now induce, say, turbulence downstream a monopile, typically there are some say, vortices that go that can lift up sediment, and that may what we see on the images. So I don't think it's probably not related directly to the scour process.
Great, thanks for that clarification. I think we're to the last slide now on talking a little bit about that interaction between what we see in the water and the atmospheric effect. Ole, do you mind, or Hans, can one of you, I think Hans started to allude to this in his slide earlier. Who wants to tackle this one?
I didn't put that slide there. Ole, it's yours?
No, but I can say something. I think what we see here, that is the wake effects from an array of turbines. Now they are in the most critical position here for this study. But say wake effects on turbines, it's a hot issue if you are for the developers in terms of energy content. The Danish Ørsted, they just lost 10% of their value because they suddenly discovered that the wake effects had a bigger impact on the energy production than they foresaw. So it is a hot issue if you are an energy producer. From the marine environment and from the water side, the effects are that we have this, say, the slower wind speeds inside the park, and of course that has an effect on the stresses and the forces on the water surface. So it goes back to the waves, goes back to the cooling, goes back to the circulation. And some of these, well, at least the future plans for development, where we have, say, 100 by 100 kilometers off. Sorry, it's my dog. Yeah. When we have these large installations, of course, it will have an effect inside these turbines. Normally, what you see here is probably, as I said, stable conditions. If you have stable conditions, these wakes, they can stay for a long time, long downstream distance. If it's turbulent, then they will disappear very quickly. Maybe not even reach the next turbine.
Great. Yeah, thanks for that. It's another aspect of, I think, something that we've across topics. It's, you know, how to deal with the variability. You know, the things are often, you know, very much dependent on the particular site. If it's extremely stable atmospheric conditions, then you will see the effect over a longer period. If it's unstable atmospheric conditions, and I think the same applies in underwater as well, you see very, very different changes. So it's all context driven. And Josh, I think, showed that even with the cold pool. Cold pool is not static. It's a dynamic feature that occurs throughout the year. While we're on some of these slides on this, I don't know, Ruth, did you want to jump in maybe about, you know, some of what Ole was referring to as like the spacing of turbines that we might see on the Atlantic, and you know, how you consider that wind wake effect? Am I putting you on the spot, Ruth?
Maybe if I was get off mute. No, so I think it's going to be interesting because, you know, there are some differences in the U.S. Atlantic margin compared to some of the European studies. And as we know, the turbines that are coming in the U.S. projects, in simple terms, are taller and larger. So taller turbines, larger turbines, right? In the Mass, Rhode Island area, there is a proposal where the wind developers have come together to look at a uniform spacing. So if folks aren't familiar, you can look at the BOEM map, but those leases are basically adjoining. And so they've come up with a 1 by 1 nautical mile spacing. And so there's some opportunity with the standard spacing like that to do some of the modeling work. And I know that some of our university partners, especially SMAST and others, are considering those types of things we can do. From our perspective as an offshore wind developer, our Med-Ocean engineers, meteorological and oceanographic engineers, are certainly starting to model this in terms of what you heard around energy efficiency. So it is a very important topic. But a lot of the data that we need, as Josh alluded to, And that atmospheric data, we may not have in terms of a robust network. So we do have to rely quite a bit on atmospheric modeling and trying to project that outwards. So that's where the data comes in. And I see Hans's question. When we get down to the mid-Atlantic in itself, those projects aren't necessarily adjoining. They're at different parts of the margin, different distances from the coast too. So coast impact comes into that, and stability. And so a lot of those factors that we have to consider, but some of them are going to be unique to the location. Others of them we may be able to look at across projects. And then spacing itself is going to be a project by project decision. So just because Mass Rhode Island, you have adjoining leases that have looked at layout, doesn't mean that other leases down the Atlantic coast are going to adopt that spacing model. So all of that kind of gets wrapped in. It was a long answer with not a very direct answer, because some of it's project specific, some of it's going to be equipment specific, and some of it's going to be based on our ability to model and project that. Hans, did you want to add?
Yeah, I just wanted to add that, I mean, the wake effect is not only a matter of efficiency that one wind turbine would shade the other one. Yeah. It is also that you kind of, as Ole said, in the entire array, you would have kind of reduced wind stress, and also in a wake area, kind of downwind of the wind farm, you would have reduced stresses. That means you also generate a wind stress shear, right? And this wind stress shear, and together with earth rotation, gives you upwelling and downwelling dipoles, which actually have a direct effect on the hydrodynamics and also on the ecosystem. And that's why I said actually that we really need to study the joint effect of the turbines in the water, which reduce stratification, and the effect on the wind stress, which generates upwelling and downwelling dipoles. And I think we are still lacking a little bit these coupled studies, atmosphere-ocean studies.
That's a great point. And it's not just in this case, but we're dealing with that with storms and other dynamics too. So the coupled atmosphere-ocean boundary are going to be critical, and what type of data that we need to collect for that, and how do we need to collect it considering where these wind farms are going to be, and at what resolution do we need the data to supplement both the atmospheric and oceanographic level.
Brian, why don't we try to maybe get a few questions in? Is that okay? And I know it's.
I was just about to turn it over to you, Pat.
Thank you. No problem. So there's a few questions that come up about, are there experimental studies that exist to validate the modeling that is used to determine some of these things? So if people are curious about the link between the modeling and actually the studies to verify or justify it, validate it.
So empirical data after the model. I don't know, there might be, I think that's what Hans was presenting on to some extent. I don't know, Hans, do you want to take that on? Were there models done?
If you go back 2 slides, then you can see that again. I mean, the lower left North Sea study, that was this recent study by Schulze et al. That is really the lower left here. I think that's really the first study, at least they say that, and it's a 2020 study, where they have these direct measurements of the turbine wake effect. And that, of course, needs to be kind of upscaled for an entire wind farm to be then compared to models. But this has to be done, right? I mean, when I did my study, that's the lower right study in the Baltic Sea, there was simply no wind farm in the Baltic Sea, so it was very difficult to validate our model, right? But now I think we have the possibility to do that because there are wind farms. The models have also become better. So I think the future will be needing that we do such data model comparison study.
Thank you. The next question is just about, there are different kinds of foundations that are being built. There's obviously monopiles, there's pylons. Has there been, there even could be the shape of the monopile itself, if it's maybe elliptical versus circular. Has anyone been studied to actually try to say that those different structures have different effects, and or that they can reduce by actually the shape that you design?
Yeah, I don't know. Ole, do you know?
That is a big issue in engineering. to look at, not for wind turbines itself or legs of a platform, but to estimate the drag forces and the impact on the water from different shapes of structures. That is a big issue, and there is a lot of data on that. And the shape is very important for the drag, but it's always a compromise between, say, reducing the forces or the drag forces and then the stability of the structure. It also has to carry some loads and be able to withstand the loads. So it's an optimization process that is actually pretty complicated. And wind turbines, etc. We do big studies that we are part of that looks exactly on how to optimize the structure, because the cost of the structure is such a big part of the economy.
Yeah, I mean, I think for context, I don't think there are very many jacketed, wind turbine arrays in European waters. Please correct me if I'm wrong, but I think there
are a few.
There are a few, yeah. That might be part of why most of the studies are focused on the cylindrical pile designs, and I think the scour is greater around the cylindrical pile designs, and that's why you see the scour protection layer being more required for those than perhaps jacketed structures. Does anybody want to talk about
that? Jacket is more expensive, so it's mostly for deeper waters.
Yeah, that's right.
I mean, from the perspective of shelf seam models, which we use to study the effect of the wind farms, this is really a subscale process, and we need parameterizations for that. And of course, for that, you need all these engineering studies and so. But for the time being, as long as we don't really know what the exact effect of various designs is, I think we can play a little bit around with the mixing efficiency, for example, right? I mean, one could kind of assume a relatively low mixing efficiency, maybe from a cylindric structure, and maybe increasing the mixing efficiency in the water if you have more complicated masts there.
Thank you. I'm going to try to get into just one more, which is actually kind of a big question, and then we'll close for lunch, which is, I think people are trying in their minds in this presentation to kind of link the kind of physiological or oceanographic effects with what actually it means for the biology. So, do we understand any of these effects, and then the effects to species, to habitat? Is it possible that if you had enough foundations at a regional scale, you could cause stratification and some kind of nutrient upwelling? So we're just trying to understand the biological impacts of this. And I don't know if people can at least just speak to that briefly before we go to lunch.
I can take a stab at that. And all of the processes that we've talked about have impacts on the ecology. A good friend of mine and colleague has taught me well about how important understanding the physical ocean is in terms of how these animals interact with their environment. It's much different than the experience that we have in the atmosphere, where they're in a very dense fluid, and many of them are ectotherms. So all of the processes that we've talked about move temperature, affect the introduction of nutrients to the euphotic zone where the sunlight can hit it and promote growth. And so understanding these features has been a focus for biological and physical oceanographers for decades because of how linked they are. And in our area in particular, I mentioned the cold pool. There are many examples of processes that are very dynamic. It changes dramatically from season to season, and the species have all evolved to take advantage of that because of that connection. So yeah, there are many examples. We benefit in our area because of the focus that there has been. We do have actually a very long time series from federal resources, academic groups, private sector, NGOs have all contributed to our knowledge of the system and how coupled it is, and it raises a lot of questions when we talk about this space.
Josh, thank you. Really appreciate it. So we are going to break for lunch. Thank you, panelists, so much. Thank you, Brian, for a great job in bringing people together, covering so much so quickly. And thanks for the great questions and my imperfection not getting to more of them. What I want to do is, Lane, do you want to just